Here is where you were stuck for the last week or so, but we're going to skip through some of the stuff that we have already covered and move to the point where we left last time. We are finding the closest pair of points. We did it for one dimension. And the version in that one dimension that we are interested in, version of the algorithm that we are interested in 1D is the one that does divide and conquer, okay? Because we can extend it to 2 dimension, which is this one. And now we are in 2D. We divide our problem using median of median or sorting, excuse me, into 2 problems of equal size. That part is easy. For each pair, for each subproblem, we can recursively find the closest pair. The problem now comes in the combine step. How do we figure out whether there is a pair closer than, so we get a pair of blue points and we get a pair of red points. And the question now is there a blue-red pair which is closer than blue or red pairs, okay? And that's the combined question. So a pair like this. If we are somehow able to figure out a linear way to combine them, then this is going to be our recurrence. We will get T of n is less than or equal to 2 times T of n over 2 plus n, which will give us n log n algorithm, right? Which is what we were looking for. Any questions so far before we move to the combined part? Right, we have seen this now. Okay, so how do we combine this without comparing each point on the left to each point on the right? If you have to compare each point on the left to each point on the right, there are half of the points on the left, half of the points on the right. That's going to come out to be n squared or 4 comparisons, which is order n squared already, right? That's the brute force algorithm that we had. By the way, note that the brute force algorithm works in any fixed dimension, okay? Brute force algorithm that we decided for 1 dimension also works in 2 dimension or 3 dimension or 4 dimension. So you already have an n squared algorithm for any fixed dimension. I'm kind of repeating a keyword here, which is fixed. Once I decide that dimension is not fixed and it's a parameter of your problem, then you are in trouble, right? Let me repeat, and then I'm going to ask you if there is a question. So as long as dimension is fixed, dimension is constant. For example, if I tell you the problem is in 10-dimensional space, you still have an order n squared algorithm. You can compare every pair of points and find the smallest, right? But once I decide that dimension is also part of the input and it's not fixed, your algorithm doesn't already know what that dimension is. It's going to know the dimension once I give you the input, right? Then you are in trouble. Then your algorithm is not order n squared. Does this make sense? Yes? Okay. Why? Why can't, for example, if I say that dimension is one of the parameters, why can't you still do what you were already doing, which is that you compute the distance between every pair of points and return the smallest one? You can still do it, right? But what I'm saying is that now your time complexity is not going to be order n squared. Yeah. It's going to be, it's going to be more, of course. Yeah. It's at least n squared, right? You have to compare every pair. So I don't want to linger on this point, but what I want to say here is that when you compute the distance between a pair of points, dimension is involved. You have to compute distance in every dimension. How do you compute distance between 2 points in 2 dimension? You take the difference of x's and y's, right? If you're in 10 dimension, you do this for 10 different axes. If the number of axes is variable, then your time to do the distance computation is also variable. Okay? All right, minor point here. So first of all, you need to observe that your closest pair is going to be either minimum of these two things or smaller. Right? It's either the smallest blue point or smallest red point, minimum of these two, or maybe something smaller. Okay? The next observation is, now you have to figure out which blue points to compare with which red points. If there is a blue point which is farther away to the left, then you somehow know that that's not a point that you want to consider. For example, if I look at this point does not seem like a point that should contribute to a closest pair. All right? Can we kind of formalize this? So formalism is that if there is a point which is at distance more than delta from L, then we don't care about that point. Okay, let me make a figure here. So I have some points on the left and some points on the right, and I have a line L in the middle. And what I'm saying here is that if there is a point which is at distance more than delta, then this point is not something that could become a closest pair with any red point. Right? Because this point is already at distance delta from L, which means the distance of this point for any red point is going to be at least delta or more. Okay? So we don't need to take care of this point. Similarly, if on the right side, any red point which is at distance more than delta should not be considered. All right? So the only points I care about are in this vertical strip, which is of width 2 times delta. All right? So far, so good. The second observation is that you can still have a lot of points within this strip. It's possible that all of your points lie in this strip. Okay? So we still have a problem. But here is a kind of a remarkable lemma, which says that if I sort my points in y direction in this vertical strip, I don't need to compare more than 11 points for each point. Okay? This is actually more like 7 points here, but 11 was kind of a lousy calculation here. So what I'm going to do is I'm going to sort my points from top to bottom or bottom to top. And when I consider one point here, blue, I'm going to compare this point with the next 7 points. And that's it. Any points that lie more than 7 points away is not going to be a distance less than or equal to delta. All right? And the reason is because of the packing lemma that you hopefully already saw. So I have this vertical strip, and what I already know is that these blue points are at distance more than delta. Right? If there was a pair here which is at distance less than delta, then I would get it in the first recursive call of my function when I was trying to find the closest blue pair. Right? So I know that all of these points are at distance at least delta from each other. Similarly, all red points are at distance delta from each other. The only possibility of a pair at distance smaller than delta is between a blue and a red pair. Okay? So what we do is we make this delta over 2 by delta over 2 square. And now I know that since the parameter of this thing is less than delta, I know that this square cannot contain more than 1 point. Okay? If I had 2 points here, then they would be at distance less than delta, because this is a very small square. right? If I have a square of size 1, 1, then every pair of points is at distance less than square root of 2. Its parameter's length. Is it called a parameter or a diagonal? What is this thing called? What's the name of this thing? Diagonal? Is there a name for it? Parameter is the hypotenuse of the triangle, but what's if this is a square, what do we call it? All right, diagonal. Okay, so diagonal's length is less than or equal to square root of 2, which means that which is the maximum size line segment in a square, right? So if you dictate that your points are at distance more than square root of 2, you cannot have more than 2 of them here. All right. Similarly, you can so if you make a square like this, you will have 1 point here and maybe 1 point here, and a 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 point here. So if I start with a point somewhere here, any points which is 2 squares away cannot be at distance less than delta, right? And I have at most 7 of these. All right? So that's the kind of final packing lemma, which says that you cannot have more than these. So more than 7 points to compare with. This simplifies our algorithm now. All I need to do is sort the points by y-axis and compare each point to the 7 next points, and see if any one of those is less than delta. If it is, then I update my smallest closest pair distance. All right? Yep.
Why the 2 points cannot lie in the same delta by 2?
Sorry, again?
Why the 2 points cannot lie in the same delta by 2 boxes? Why cannot 2 points?
Right. So is asking the question about the packing lemma. Why we can't have more than 2 points in the delta by 2 square?
More than 1 point.
More than 1 point. So you can have 2 points at the boundary. That's what you can have, right? But if I'm starting with, you can have at most 1 point, right? Because so assume that this is delta over 2 and this is delta over 2. The length of its diagonal is, what is it? Yeah, it's delta over square root of 2, right? So it's smaller than delta. I already know that you cannot have 2 points at less than delta distance, right? That's the reason I cannot have more than 1 point here. Okay, so remember that I strategically created these boxes either on the left or on the right. Okay, which means that I'm going to have only blue points on this side and only red points here. And all blue points are at distance delta, which means that each square is going to contain at most 1 of them. Yep.
How did we use this to prove कि 7 से ज़्यादा नहीं चाहिए?
So I'm sorting my points in y-axis, and I know that if I go 2 blocks up, that point is going to be at distance more than delta. So I'm not interested in that point. Okay? And within this 2 blocks distance, there are 7 points that I need to compare with. So if I am this guy, if this is the point I'm looking at, then I have to check with this guy, this guy, this guy, this guy, this guy, this guy, and this guy. This makes 7 points. Yeah?
Wouldn't we use the same logic horizontally? जैसे हम ऊपर 2 boxes से आगे नहीं जा रहे क्योंकि more than delta, तो horizontally हम 2 boxes से आगे नहीं जा रहे.
हम नहीं जा रहे 2 boxes. So we are using both horizontal and vertical distance. This is the horizontal distance thing, that I'm not going to go more than 2 delta in this direction, and I'm not going to go more than delta in this direction. Right? We are using both of these. artifacts. Yep. No. So diagonally, your distance can be at most. So here is a possibility, because you can have a point right at the edge here. And for this point, each of these points is kosher. Right? Each of these points can possibly be at distance delta, less than delta.
So what about we have a point in the bottom left
Okay.
corner and then the top right corner?
Right.
One in the blue region, one in the red region.
Right. So I'm not saying that these points will have distance less than delta. What I'm saying is potentially these points may have distance that's less than delta. Okay? So these points are not guaranteed to be at distance less than delta. There's definitely, you can place points which are at distance more than delta. That's going to happen. What I'm saying is that it's possible that they are at distance less than delta. And that's why what I'm doing is I'm checking each point with all 7 points. If any one of them is less than delta, then I'll update my smallest distance. Right? Yeah. Again, it's not guaranteed that I'm going to find a point which is at distance less than delta by doing this. Right? Awesome. So this concludes the closest pair thing in 2 dimension. I think we have the runtime complexity analysis. Before I go to the slide, I would like to do it myself with your help. So this is what we agreed on. We said that this algorithm will have time complexity. T of n is equal to 2 times T of n over 2 because of the 2 problems, 2 subproblems. Size of the subproblem is half plus. If I could get linear here, this would give me what? What is this? If I could get this, what would be my time complexity? Yeah. This would give me order n log n. Right? But do I get here? Is this the cost of combine? What's the cost of combine? The process that I just described. So let me remind you, what you do during combine is you restrict, you find out the points that lie within the 2 delta strip. Okay? So you compute the distance of each point with the line and find if the distance is less than delta or not. If it's less than delta, you keep it. If it's more than delta, you throw it away. This is one thing that you do. And the second thing you do is, once you have those points in the vertical strip, you sort them by y-axis. Right? So these are the 2 things that you do in the combine. Or uske baad, the next thing is simple. What you do is you loop through it, and for each point you compare it with the, well, actually that's a significant step as well. Let me write it down. So first step, remove points at distance more than delta from your line L. Right? This is what you do. Second thing, you sort them y. Sort by y-axis. And third thing, compare compute and compare distance between I and j, where j is less than or equal to I plus 7. Right? These are the 3 things we do. Now you're going to help me figure out how much time I'm spending doing this combined thing. How much time to do step 1? Raise hands. Constant per. It's not constant. I'm removing all the points which are at distance more than L. How long would I have to spend to do this? Okay. You have to loop through all the points, right? Right? So that's N. All right, second step. This one is easy. N log N. And the third one? Yeah. So Cn again. Okay? But here's your trouble. You got N log N instead of Cn. So your time complexity becomes 2 times T of N over 2 C times N log N. Okay? How do you solve this? You solve it using a version of master theorem which says that if f of n is kind of extension of master theorem that you know. If f of n is theta of n to the power log b of a log n to the power k, where k is anything more than or equal to 0, then your T of n is, does anyone know this? No? All right, it's the same thing with an extra power of log. Okay, so this is n to the power log b of a k plus 1n. All right, so this gives me order n log squared n. Okay. Yeah. How are we choosing our delta? Our delta is coming from the recursive calls that we make. So this is what we were doing, right? So we found the smallest pair in blue and smallest pair among red pairs. Smaller of them is the delta. So minimum of these two numbers is my delta. I have not, because I have only checked blue pairs and red pairs. Right. That we have to do during the combine step. Combine step is actually where we do all our work, ultimately. All right, should we move on? This you should know, this part of the master theorem, because I have discussed it now. But this gives you order n log squared n. I think some of you should already be able to figure out how to kind of reconstruct this and do it in n log n time. Okay? Just keep this as an exercise. If you fail to see why this is true, you should go to, I think it's in the book as well, but Subhash Suri's notes are more intuitive. I think he also discusses the 3-dimensional case. Anyhow, that's the conclusion of closest pair. Last week we were discussing counting inversions, and we also had an n log n algorithm for that. Someone asked on Slack, we started with an order n square algorithm, right, for inversions, also for closest pair, which was the brute force algorithm. And then we said, let's improve on it. Let's find a better algorithm if we can. And we did, for inversions and for also closest pair. So the question they asked was, why stop there? Why not try to figure out a still better algorithm which does better than n log n for inversions, or n log n for a closest pair? Anyone would like to venture a guess why we don't do that? or at least why we don't teach that. I guess we do. Go. Okay, cool. That's what we are going to do. We are going to prove that you cannot do sorting in less than n log n time if you are doing comparisons. Okay, and that kind of implies that inversions cannot be done in n log n time. That also implies that closest pair cannot be done in less than n log n time. I'm not doing those implications; they require a bit of work. But the first part, sorting lower bound, वो अभी हम कर लेते हैं. Okay, sorting lower bounds करने से पहले I need a couple of tools from I guess data structure. So let me just outline so that you have them in the back of your mind. So a binary tree is a tree. I assume you already know tree. We'll define it later when we do graphs. But for now, tree is what a tree was in data structure, with a fixed root node and every parent has what? What do we know about binary trees? Every parent has. At most was the keyword I was looking for. At most 2 children. And so this is kind of definition. The fact I'm going to use is that if a binary tree with height h has at most leaves. Can someone fill this up? So a binary tree with height h has at most this many leaves. Is it? Yeah? Yeah. So depending on how you define height, but for our discussion, it suffices that this has 2 raised to power h. If you include so if this guy has height 0, then you would end up with 2 raised to power minus 1, right? So that's why I'm going to just do this. Okay? I'm going to assume that this guy has height 0, so you have at most 1 leaf. Okay? So that's what I'm going to use, okay? You cannot have more than 2 h leaves if your height is h, because you're doubling and that's the restriction of the structure. Anyhow, okay, so we want to understand the fundamental limitation of sorting. Note here that I'm emphasizing on the fact that we fix that our algorithm is going to use comparisons. Okay, so can we sort faster than n log n using comparisons? And what is allowed? What's the comparison model? Comparison model is that you're allowed to compare 2 elements, any 2 elements, and based on that decision, you do something else. That's what your algorithm does. That's what all of your algorithms, which are comparison based, do. Bubble sort, merge sort, quick sort, heap sort we didn't discuss, but this is what they do. Okay, they compare whenever they are computing, for example, rank. What they're doing is they're comparing elements. Okay, and based on that comparison, they're figuring out what other comparison do I need to do next. Okay? Which means that any comparison-based algorithm can be written as a series of comparisons. Is that right? So let me kind of rephrase that. So every comparison-based algorithm, sorting algorithm, can be written as a series of comparisons. That's one possible model of that algorithm. All right? With one critical distinction, which is that it's not a series, it's a branching. For example, I think I have a picture somewhere here, which is this. If I know the result of comparing A1 and A2, I might next compare A2 and A3. And based on that comparison, I might do something different. I might, for example, look at the left branch. At this point, I am, for example, if A2 is less than A3, then I am already done with the sorting. I already know that A1 is less than or equal to A2 is less than or equal to 3. But if A2 is more than A3, then I have to do more comparisons. Okay? So it's not a series, but it's a tree of comparisons. Because based on a comparison result, you do different things at times. All right? So I can represent my comparison algorithm as a comparison tree. This thing is called a decision tree, because instead, you don't just have to do comparisons. I'm doing it for comparisons, but you can do anything in here. But this is what comparison tree looks like when I'm trying to sort 3 elements. All right? So in this comparison model, the nodes, all my nodes except leaves represent comparisons, and the leaves represent the final sorted order. All right? So in this example, number of leaves is equal to 6, right? If I had 4 elements, how many leaves would I have? Reasonable guess? Wrong, unfortunately. 8 is not the answer. Okay, 16 is not the answer. Let me just make sure it's not. Yeah, 16 is not the answer. Remember the third or fourth bullet point here. What does it say? So leaf represents final sorted order. The question is, if I had a comparison or decision tree with 4 elements, how many leaves would I have? 24. 24 is the answer. And why is that?
4 factorial.
Yeah, 4 factorial. So you can have all possible permutations when you're trying to sort a list of 4 numbers, right? Since there are 24 or 4 factorial permutations, you will have this many leaves. Is this clear? So if I have n elements and all of them are distinct, then I'm going to have n factorial leaves. All right. That kind of solves my problem. And what's my problem? My problem is to count the number of comparisons that I have to do a sorting, right? So can anyone tell me the next thing I should write on the board? So you just told me that the number of leaves in this ugly tree is equal to n factorial. All right? What should I do next? What does that tell me? I think it's a fair question. I think it's a fair question. So think about it. So the question is, what's the next line I'm going to write on the board? That's the question. Go. Can we do better? Okay. Okay, good. Fair. Okay. So, okay. My movement is restricted today. Kind of. All right. Here. So, the answer is somewhere on the board. What's everything we know about the binary trees? These are binary trees, right?
We create a root node to compare the first and second value. Is that similar to the one we have on the board?
Okay. No. I really want you guys to do this. Yeah. Make the tree? I'm not going to make the tree. No, that's going to take me 5 minutes. I'm not going to make the tree. That's why I spent, I don't know, half an hour making this tree. So that, yeah. Yeah, that's what I'm going to do. Anyone else? I thought there would be at least 5 people who would figure that out. So from that slide, from that board thing, I know the relation between the number of leaves and the height of the tree. Okay? And now I know the number of leaves in this tree. So I can bound the height of this tree. You know? Yes? All right. So I know that the height, so I know the number of leaves is less than or equal to, what is it less than or equal to? 2 raised to power h. Right? This is what I know. So n factorial is less than or equal to 2h, which means that h is greater than or equal to log of n factorial. Okay? And log of n factorial is n log n. So I know from this bit of calculation that the height of comparison tree is at least n log n. Okay? And what does the height of the tree represent? What I'm doing at each level. I'm doing a comparison. Okay? So if my height of, if the tree height is 3, then I'm doing at least 3 comparisons. Right? So this concludes that the number of comparisons is at least n log n. No matter how I design my algorithm, if my algorithm does comparisons, then it's going to look like a tree. Then I'm going to have to distinguish between n factorial possible answers. I must, right? If I have to distinguish between n factorial possible answers, then I'm going to have to make at least n log n comparisons. Cool? No? No? Okay. Awesome. So, what do we do? Any questions before we move on? Yeah. So n log n is the log of the n factorial. I think you guys did this in the homework 1. Did you? Log of n. So n factorial is, you want me to do it? It's going to take me 10 minutes, I guess. Let's see. So this is n factorial. N into n minus 1 into n minus 2, 1. So, and I have to take a log of this thing, right? This is going to be more than or equal to if I only do it for the first n over 2. So it's going to be log of Yeah, I want to do it. So it's that. So I removed the last half terms, okay? And I did greater than equal to. So this is equal to log n over 2 to the power n over 2. And this is equal to n over 2 log n over 2, which is a constant times n log n. Right? This is what I did over there. Oh, it took me a couple of minutes. I thought it's going to take me 10 minutes. Anyhow. Questions? Questions? Yeah. Okay, I guess I missed a step. So right here there is a step which is that I do greater than equal to log of n over 2 times n over 2 times n over 2 n over 2. So I replaced everything more than n over 2 with n over 2. Right? So I had n over 2 terms here. Each one of them is more than n over 2. I can replace all of them by n over 2 by writing greater than equal to. Yes? All right. Yeah. Which part? Why I am doing what? Use n over 2 because it helps me. It makes things simple. I could have done, what else could I have done? Anyone else has any other ideas to fix this? So I could have done 3n over 4 to the power n over 4. That would have done it for me. I need anything, a fraction of n here to the power a fraction of n here. So n over 2 is, I think, the simplest thing I can do here. I do something different on the slides, I think. So what do? I do this. So I use the Stirling's approximation. Using Stirling's approximation, I know that n factorial is something like square root of 2 pi n and n over e to the power n. Everything except n to the power n goes away, becomes a constant. So I end up with n log n. Right, so multiple ways to reach the same solution. Questions? This part is important. I want you guys to understand this because this is the only lower bound thing that we have done this in this course so far. So in that context, it's important. You should know. Yeah. N log n is.
So as in n log n is the lower bound and n factorial.
Right. Yes.
Why did you write beta and not beta?
So it turns out to be it's also an upper bound as well. Yeah, this part is upper bound as well. For this work that we are doing, you are all right. हम यहाँ पे इसको ऐसे लिख सकते हैं. हमें लिखना चाहिए. But in general, what I wrote was not incorrect because log of n to the factorial is upper n lower bounded by n log n. Right? Because you can make all of them equal to n and they become n to the power n, which is also n log n. It's also greater than or equal to and smaller than equal to n log n. Yeah.
ये simplification की अभी तक समझ नहीं है कि how did we go from n factorial to n log n?
How did we? We took the log of n factorial. We took the log of n factorial. And this is the definition of n factorial, right? I replaced n. So at this point, I truncated everything beyond n over 2. उसके बाद फिर I replaced everything with n over 2. ये वाला. So यहाँ पे देखो everything except n over 2 is more than n over 2, which means by doing this I can replace it with n over 2. Right? So this is what I am doing. I'm writing log n is greater than log n over 2, which is correct, right? Log n minus 1 is greater than log n minus 1. So this is what I am doing. I am replacing everything which is more than n over 2 with n over 2, just to help simplify things for me. Right? Yeah. Sorry, once again? Because there are n over 2 terms like this. So you have n over 2 times n over 2 times n over 2, n over 2 times, then it's n over 2 to the power n over 2. All right, so any comparison-based sorting algorithm on n distinct elements requires order n log n comparisons. To beat n log n, you must do something else, which is you must leave comparisons out. You cannot use comparisons to do the sorting if you want to spend less than n log n time. So we have sorting algorithms which beat n log n bound, but they use something about the input that's beyond what we already assume. For now, we assume that our array contains numbers which are constant width. They assume something more than that. So, for example, counting sort, I think we are going to see, is going to take order n plus k times, and the assumption is that every number that we are going to use for sorting, or the key, is smaller than or equal to k. All right? आप दोनों आगे आना चाह रहे हैं, आप आ जाएं. Yep. आ जाएं हरी आप. मनीष, ये लोग भाग जाते हैं यार अगली क्लास में, इनके नंबर लो यार. इनके तो नंबर ले सकते हैं. Make sure they sit next to me. बाकी लोग कहाँ पे हैं जिनको मैंने बुलाया था? आप दोनों हैं? Where's the third guy? Oh, you're here. Okay. Reassuring. Okay. All right. So once again, sorry, but no. You're the chief guest, man. First row. Okay, you're not gonna sit anywhere. Okay. What's your name? Hadi. Okay, great. So Hadi tells us that if we assume that all of our numbers are less than our fixed number k, then we can sort them in n plus k times without doing any comparisons. Okay? You guys have already seen counting sort, right? Iteratively. We're gonna quickly go through them. So a sorting algorithm is, so I need a couple of definitions again. One of them is stable sort. A sorting algorithm is stable if it leaves the order as is for a pair of numbers which are equal. Okay? So essentially it's a weird way to say this, but if I have 1, 3, 3, I don't know, 0, then my sorting would be, my sorted order would be 0, 1, 3, 3. But a stable sort makes sure that this is the 3 that came first, and this is the 3 that came second. Okay? It does not change the order of elements whose keys are equal. This turns out to be important at times. Okay? Stable sort. All right. At times, this you cannot guarantee this. Okay. At times, your sorting algorithm is not stable. It cannot guarantee कि जो keys equal हैं वो same order में आएंगी. Okay. But at times you can, and for something like Radix Sort, that becomes important. The second definition is In place sort, it's here because it's cousin of stable sort. But what it says is that an algorithm is in place if it does not use more than a constant amount of extra memory. Okay? So it does the swapping in comparisons within the array जहाँ पे वो पहले से थे. If you remember the quick sort algorithm that we did a couple of variations. उसका जो पहला variation था, that was not in place. उसके अंदर we create new S and B, I guess. S array and a B array. जो उसका दूसरा version हमने किया था जिसमें we had 2 pointers and we were moving numbers around. We had smaller array to the left of the original array and bigger array to the right of the original array. That's in place sort. Anyhow, I thought I would mention this. So on high level, counting sort is this. So you input an array of integers. You assume that each one of them is less than or equal to a number k. Now you count how many times each value appears. And then you just place those counts where they were supposed to be in the sorted order. All right? So let's see how this happens without comparisons. You have 8 numbers there, and all of them are less than or equal to 5, which means your k is 5. You declare a count array. In this new array, what you are going to do is you are going to find the count of each of these elements. You already know that there are going to be at most k numbers, so you can declare an array of size k, and for each one of those, you can count how many times the number appears. So for example, you can count how many times 0 appears. Do you see a red dot somewhere? Oh, it's there. So you count how many times 0 appears, you count how many times 1 appears, you count how many times 2 appears, and so on. Okay? So you see, you do a loop over the original. Oh, it's gone again. Do you see a red dot? I don't. Oh, it's there now. Okay. I should keep it pressed. So you see a 2. What you can do is you go to 2 and you increment its count. So you start with an array which has zeros, which means that every count is 0. You see a 2, you go and increment 2, like this. You see a 5, you go and increment 5's count. You see a 3, you go and increment 3's count. You increment 0's count, you increment 2's count, 3, 0, and 3. That's your first pass of the array. Okay? How much time have we spent so far? Hadi, how much time have we spent so far? Oh, fine. Yeah, we have just did one pass of the array. Okay. What's next? So now what I could do is it's a stupid thing to do, which kind of sounds like reasonable. So I have this count array, which is zero, 2. Count of 0 is 2. Count of 1 is 0. Count of 2 is 2. Count of 3 is 3. Count of 4 is 0. And count of 5 is 1. All right? Here is a kind of stupid but kind of correct thing to do as well. So what you do is you go read your count array. You see 2 zeros, so you put 2 zeros. You see 0 ones, so there's no reason to put 1. You see 2 twos, so you put 2 2. I had 2 twos and 3 threes. Wow, okay. 3 threes. 0 fours, so no fours. And 1 5. And that's your sorted array. Right? Reasonable, right? Yeah. So And it is reasonable, but the problem is this is not stable. Right? You're not sure that this first 0 is the 0 that appeared first in the original array. That becomes important somehow. But this is essentially what counting sort is going to do ultimately. Okay? So what it does next is it creates prefix array from the original count array. So it's going to create the index for each number. So what it does, अभी तो जो काम हुआ है वो बहुत आसान है. What it's going to do is it's adding things up. So 2 को वहीं पे रख लिया, 2 और फिर 0 को add किया, and you get a 2. And then you add 2 plus 2 and you get a 4. I don't see the red dots anywhere. No. Okay. Then you add 4 and 3 and you get a 7. You add 7 and 0, you get a 7. You add 7 plus 1 and you get an 8. Everyone on board how we get the prefix array? I'm starting in the beginning and then I'm just adding things up. And answer at each step is in the green box. So that's that. And it represents how many elements I'm going to have less than or equal to that number. So I have at most, I have less than or equal to 2 numbers which are less than or equal to 0. Okay? So the second 2 says that I have at most 2 less than or equal to 2 numbers which are less than or equal to 0. Okay? This 4 says that I have less than equal to 4 numbers which are less than or equal to 2. Okay? Any questions so far? No? I'm just going into random details, right? Okay, so once you have that, you can do sorting, which is to get this array. How do you get this array? I should have added a animation there. Anyhow, so the second loop tells you how to get the prefix array, and then you loop through your numbers in the reverse order and put your numbers where they are supposed to be. Okay? So let me kind of quickly do this. I thought I had a complete animation there. Okay, let me just do this from this point onwards. So, yep, to make sure it's white. So, to get the prefix array, I'm gonna get a 2 here. 2 plus 0 is 2. 2 plus 2 is 4. 4 plus 3 is 7. 7 plus 0 is 7. And 7 plus 1 is 8. And now what I'm going to do is I'm going to place 5 at the 8th place. So I'm going to create an array of length 8 now. And I'm going to place so I'm going in the reverse order in the original array. Where is the original array? Right. So I'm going to look at 3 in reverse, and I'm going to find the first index of 3 should appear at 7. So 8, 7, 6, 5, 4, 3, 2, 1. I think 1, right? I don't have a 0. Okay, so I look at 3. 3 is, the last 3 is at 7. So I'm going to put a 3 here, and I'm going to decrement this number. I had a 7 here, right? Okay. 6. Okay, next I see a 0. I go to 0th index. And it says that I should put 0 at 2. So this is the 0. So remember that I'm putting this 0 here. This is important. Should use the yellow here, okay? Which means that I leave place empty for this 0 before this. Okay, that's the important part. Anyhow, what's the next thing I see? I see a 3, and I go to this index. मैंने 0 के against decrement नहीं किया. So I come here, and this says that you should put a 3 at 6. So I'm going to put a 3 here at 6 and decrement this number to 5. Then next I see what do I see? 2. So I go to 2. This says put a 2 at 4. So I'm going to put a 2 here at 4 and decrement this number to 3. What do I see? I see a 0. Now I messed it up, right? This 0 was the 0 that's next to 3. Okay, this is not the 0 from the count array. 0, should write last 0 in input, right? And what do I do next? Where am I? I have put the first 2. I have put the, next is 0. So 0 is 1. I'm gonna, this becomes 0. This is 1. And next I have a 3. 3 goes to 5. Did I mess up anything? I think not. This is the final sorted array. Which one? This one? Here? This index should be 0? This value should be 0. Oh yeah. See, I knew I was doing something wrong. Anyhow, okay, so then I see 3, I put the 3 there. Then I see 5. 5 goes to 8, so I'm going to put a 5 here. This becomes a 7. What's next? 2. And 2 goes to 3. Okay. And it comes here. Okay? So it works the way we tried to do it earlier, the simpler version. But this makes sure that what you are doing is stable. That the last 0 appears last and the first 0 appears first in the original sorted array. Okay? Should we quickly move on? The time complexity is super clear, right? You have a question? Yeah.
What if original array contains negative numbers?
It doesn't really matter. So, but it's a good question. The question is, what if the original array contains negative numbers? Anyone has any idea how would that work? If I had an array which contains negative numbers, how would I do counting sort on that? Absolute value is bad because it reverses the order, right? So if I have a -5 and I have a 4, taking absolute value will make it 4, 5, which is not what I want, right? What else could I do? Absolutely. So that seems like a simple answer. Okay, you have an answer?
Find all the negative numbers,
Yes.
sort them,
Okay.
and then reverse that array, and then join it with the positive numbers.
That could work, but this thing is simpler and easier to do, which is that you find the smallest negative number, and you add that number to everything else. So if you have, for example, -4 and -25, 0, and 2, so you add 25 to everything else, and you would get Oh gosh, what do you get? 20? Yeah. And 29? Assuming that's true. 0, 25, and 27. All right? And once you are done with everything else, you subtract negative 25 from everything else. Okay. Working weekly. So these tricks work, even your number, if you have negative numbers, as long as the range of numbers is small. So time complexity, I was writing down, of this algorithm is order n plus k, where n is the number of elements and k is the range of elements. If your numbers are starting from 0, then k is the largest number. Okay? So if you have an array which contains 0 and a number which is 10,000, then you have only two numbers, but your algorithm is going to take 10,000 steps to sort those numbers. Right? Would not be an appropriate algorithm to sort it. Okay? Questions? What is an appropriate situation to sort using counting sort is something called Radix Sort. Let's quickly go through that as well, if there are no questions. Yeah. I see the greedy eyes. Yeah. Sorry, what? What is k here? K is, if your numbers are starting at 0, k is the maximum number in your keys. But if you have negative numbers, then it's the range of your interval. So in this case, for example, your largest number after you have done the shifting. Any other questions? Okay, let's do Radix Sort. So, yeah, you need to come up with a question if you want to stop me at this point. Yeah. Yeah. Because what I'm doing is the size of this array. So the question is, why does k show up in the time complexity? Okay. The size of this array is k, and I fill up this array by doing an order. Okay. You need to be more creative with your questions. No? Let's do Radix Sort. I'm going to do Radix Sort in the next 2 minutes. All right. So I just mentioned that I actually don't have slides for Radix Sort, so I'm going to do it on the board. All right, so what is Radix Sort? I'm going to take 30 seconds to remember what Radix Sort is. Yeah, so remember, counting sort works when your keys are small, or at least in the small range. If I guarantee that your keys are within the range of, well, always less than 10, then counting sort is going to do amazing. Hai? If you have 1,000,000 numbers and all of them are between 0 and 9, then you are doing great, right? Then you should do counting sort. But what if you have this? You have numbers which are between 0 and 1,000. So you have a number which is 2, 1, 3, 3, 1, 2, just 1, 2, 90, 99, 912. Then your numbers are not in a small range. Okay? But what you could do is you could stable sort based on the smallest digit index, and then you sort based on this and this. Since your algorithm is doing stable sort, this will sort your numbers. So let's do this. So after doing a sorting based on the first digit, I'm going to get a 90 at the top. What do you get next? You get 312, and then you get 12, and then you get 92, I guess. 912, sorry. 912. 12, as you see, is my favorite number. 213 and 99. Right? That doesn't do us much good, huh? So what we do next is we are going to sort it based on this second index. So what we get is all right, sort based on the second index. So you are going to get 312 at the top, and then you're going to get just 12, and then you are going to get 912, and then you're going to get what? 213, and 90, and then 9, 9. And now you sort on the last index. I'm going to finish in the time I'm given. So sorting based on this, you are going to get, oh, did I mess everything up, Hannah? Hannah? No, we are good. We are good. So you need to see that this is a 0. Okay? So you would get 12 at the top, and then 090, 099, and 312? Or 213? You're with me, awesome. 213, what's next? 312, and that's it, right? 912. That makes me happy, right? What's the time complexity of this algorithm? It's the time complexity of the counting sort times the number of digits. So your time complexity is d times n plus k. But you know your k now. Your k is 9 or 10. So your time complexity is all right? We did Radix Sort in 90 seconds. Okay, I think that's where I'm going to stop. Otherwise, you're going to kick me. D is the number of digits. All right? So if you have 1,000 digits, then D should show up here. Okay. Yeah. See you on Monday.